All right, hello everybody. Welcome to my first video in my BC Calculus series. In this series, I'm going to be going over every single lecture and slideshow that I have done for my BC Calculus course. So it says day 3 here, but that's because the first 2 days were just review and prerequisites, and today we're actually starting the real calculus material, so I'm going to start recording supplementary videos that compensate for if you didn't make a lecture, you can watch this and you'll get the same content that people were given in class on the Zoom. And also, if you just want to watch this in your free time or anybody can watch it, it will give you all the information you need to know about each topic. If you watch all the videos in this video series, you will have all the information you need to do well in BC Calculus. You'll have all the necessary information. Because what this series does is it goes through all of the information covered in the BC Calculus textbook, at least for Newton South. So if you watch this video, you are getting a solid BC Calculus education. So without further ado, let's get started. I just want to triple check that I am recording. I am indeed. So we're going to get started with our very first lesson, which is part 1 of limits and continuity. Day 3 of our lecture of my class covers limits and continuity. So I'm going to make a video going over day 3, but it only covered half of limits and continuity. So the next video will cover the second half, which I will make tomorrow after I have done my lecture for the people on Zoom. I will record another video going over the content covered, similar to what I'm doing today with the lesson that I taught earlier today. All right, so in this video, we're going to be discussing the following topics. We're going to be discussing what we mean by rate of change. We're going to answer the following questions. We're going to answer what is a limit, how do we calculate them, and how do we evaluate them given a graph. We're going to go over limit properties and limit rules as in terms of why they work. I'm going to explain that as well. Limits involving infinity, we're going to talk about in a second. We're also going to talk about how we should think about, I skipped for a second, talk about how we should think of infinity, because infinity is probably something you've heard of, but I want to make sure that we understand what we're talking about when I use that word. And we're also going to talk about something called end behavior models, which we'll get to later on in the video. All right, so what is the rate of change of a function? The rate of change of a function at a point is simply how quickly the height of the graph is changing around a point. To illustrate this, what I'll do is I'll go into Google Jamboard, and I'm going to draw a graph and some function. All right. So if we said the rate of, I'm going to draw some random function here. If we said that the rate of change of the function at a certain point tells us how quickly the height of the graph is changing, we can already get a feel for what the rate of change is going to look like if I point to certain points. For example, if I told you to tell me, describe the rate of change of the function at this point, you would tell me, well, the height is changing pretty quickly around this point. It's increasing pretty steeply around this point. So I would say this point has a high rate of change if we're looking at the function at this point. If I looked at another point, for example, I looked at this point, you might tell me that this point of the function has a lower rate of change. The function is changing, or the height of the function around this point is changing slower than it is at other points. So we might say it has a low rate of change. So when I say rate of change, all we're asking is if I ask you to find or tell me or describe the rate of change of a function around a certain point, all I'm asking you to tell me, or all that any problem will be asking to tell you, is just you have to answer the question: how quickly is the height of the graph changing around that point? Another thing that I'll add here is that with this function, it's easy to notice that the rate of change is not the same everywhere. If you look at different points, the rate of change is going to be different. For example, here we notice that the rate of change is less than the rate of change at this point. The height changes quickly here not so much. So for some functions, the rate of change will be different depending on what point you evaluate. For other functions, conveniently, that will not be the case. And the most iconic example of this is a linear function. You'll notice that how quickly the height of the graph changes is the same at every point in a linear function. They have the same steepness. Their height changes at the same rate. So that's what rate of change means. I'll go back to the slideshow. I don't know why it exits every single time. Oh, wait, because I had to exit in the first place. Some functions, like I said, like lines, have the same rate of change at all points. Other functions, like quadratics, have different rates of change depending on the point you're looking at. I'll very quickly draw what a quadratic looks like. If you look at the right side of a parabola, it's going to look like this. And you'll notice that the rate of change at this point is greater. The height is changing quicker than the rate of change here, where the height is changing not as quick. So the rate of change for some functions can be different depending where you're looking at. All right. All right, a graphical representation. As a graphical representation, the rate of change of a function is its slope. This makes sense given the slope tells you how fast the graph increases or decreases. So let's look at a linear function because that's the easiest one to deal with. We know that every line has a slope, and if you want to calculate the slope, you take you take 2 points, and you calculate the rise, how much it goes up, and divide it by the run, how much it goes across. And that will tell you the slope of the function. And we know that lines with a large slope are steep, and lines with a low slope are a little more shallow. The slope for lines is a great way to tell you what the rate of change of that function is, because we know the rate of change at every point in the line is the same, like we said earlier. And the slope tells you, if it's a big slope, it tells you, well, the rate of change is big because the height is changing quickly. If it's a low slope, then the rate of change is low because it's not changing quickly at all. So the slope for lines gives you a direct indication. The number gives you a direct indication of what the rate of change of a function is, which is why we often use slope and rate of change interchangeably. In fact, let me erase this. I'm going to say ROC for rate of change. We say that slope and rate of change are just two sides of the same coin. They represent the same thing. The slope is a direct representation of rate of change. Whatever the slope is indicates whatever the rate of change is. A higher slope, the graph is changing quickly. Lower slope, the graph is not changing quickly. All right. So the only issue is we define the idea of rate of change as applying to all functions. Like, remember earlier we described the rate of change at different points of some weird function, right? So we can describe rate of change with nonlinear functions. We can talk about rate of change with nonlinear functions like we did earlier. But the problem is with nonlinear functions, we don't know how to calculate the slope. So if I asked you to tell me what the rate of change of the function is, or give me a number that corresponds to the rate of change of the function here, with our current knowledge, you wouldn't be able to. Because we don't know how to calculate the slope of non-linear functions. And in fact, it seems like we can't at all. I mean, how on earth would we calculate the slope of a non-linear function? Like, it doesn't really have a defined slope or a defined steepness. It changes all the time. So I want you to keep that in your back pocket because we're going to go to that tomorrow and in the beginning of Unit 3. But the idea is, the idea I want you guys to be comfortable with is that the rate of change of a linear function is its slope, and the idea of slope directly corresponds to rate of change. So what we're going to do tomorrow is we're going to show how we can extend our definition of slope to nonlinear functions. How we can use this idea of slope and make it work for nonlinear functions. How we can apply it to nonlinear functions, because right now it seems like we can't find the slope of a nonlinear function. But tomorrow we're gonna see a very neat way to find the slope of nonlinear functions around certain points using calculus. So that's a sneak peek for tomorrow. Limits, what are they? Limits ask the following question. What value does a function approach as our inputs get closer and closer to a certain value? We will visualize this in just a moment. So we have a limit notation here. I'm going to return to this slide. What I'm going to do is I'm going to go to our Jamboard to kind of illustrate what it is here. All right. So let's say I'm drawing some random function. All right. And we'll call this function f of x. And let's say I'm looking at the function around x equals 2, for example. And let's say this function at around x equals 2, let's say at x equals 2, this function equals 2, as y equals 2 at around this point as well. All right. So the limit asks the following question. What value does the height of the graph or the value of the function tend towards as our inputs or our x-coordinates get closer and closer to a certain input? So if I asked you what the limit of this function was as x goes to 2, what it's asking is, what value does the graph approach from either side as our inputs get closer and closer to 2? And you'll notice that if we follow our graph and get closer and closer to 2, our graph, the height of our graph gets closer and closer to the value y equals 2. So we'd say that the limit is equal to 2. All right, this is a pretty introductory example. I will note with another example, and I'm going to use a linear function to describe this, The actual value of the function at a certain point doesn't matter. Let's say we're doing y equals x as the function we're evaluating. All right, and this is x equals 3, right? Let's say we have the line y equals x, but we're going to make it so that it's undefined at x equals 3, meaning that at x equals 3, there is no output. It doesn't have an output. There's a hole here, all right? If I asked you what the limit of the graph was as x goes to 3 of this function, we know that if it were defined, it would be the height would be y equals 3. And you can notice that even though at x equals 3, the graph is undefined and it doesn't have an output, the graph tends towards, on either side, it gets closer and closer to being 3. Even though at the actual point it's undefined, the graph still tends towards the value of 3. So we don't care about what the actual value of the input is at that point or the output is at that point. All we care about is the value that the graph is tending towards. So even though this point is undefined here, we would still say that the limit is equal to 3 because we only care about what value the graph is approaching. All right. Additionally, with another example, even if I had a line, for example, that had a hole here, and let's say it's the same line, it's y equals x, all right? But at one point, we'll say at point x equals 2, the graph is defined that at x equals 2, the output is 10, all right? So what our graph is a weird function where y equals x for every value except for x equals 2, and at x equals 2, our output is 10. So we get a jump here, all right? So in this case, the function at value at 2 equals 10. But if we asked ourselves what the limit of our function was as x goes to 2, it would still be, so if it would still be, this is a different example, we're evaluating the input 2 here instead of the input 3 from before, it would be 2. Because even though the value at 2 is 10, the graph is still approaching or tending towards the value 2 from either side. So this is just a reiteration of saying that limits only care about what value the graph is going towards, not what the actual value is at that point. I hope that makes sense. All right. So returning back to limit notation, what this means, if we write this, we write a limit, what this means is that we're evaluating the heights that the graph f of x approaches as our inputs get closer to some number a. And we say that whatever height it's approaching, we say that has a height of L. We're just giving variables to represent a general case for limits. This means that as our inputs get closer to A, f of x gets closer to L. We only care about what it's approaching. This is what I've said before. You can read it if you'd like, but it's just a reiteration of what I was saying previously. All right, so here we have some limit properties. I'm gonna go through them on a Jamboard. But they're pretty easy to understand as long as you follow along what I'm going to lay out just here. I want you to imagine, I'll backtrack here for just 1 second. I want you to imagine certain functions in a certain way. Let's say you had some function, h of x, that was defined as the sum of 2 other functions, all right? We see these kind of functions all the time. For example, y equals x plus x squared. This function is equal to the sum of 2 functions, x and x squared. I want you to think of this function, when you're graphing it, as graphing the 2 individual functions on their own. So I would take x, and I would take x squared. And then to get your new function, just taking whatever the height is of both the functions at each point and adding them together. And that's how you get your new function. I don't know how it's gonna look. I drew it poorly. I can go into Desmos. Actually, that's what I'll do. I'll go into Desmos. We got a function x squared, and then x squared plus x. I want you to really imagine that at each point, what you're doing to get our blue function, which is x squared plus h plus x, is adding the 2 heights of the individual functions. You'll notice that the height of the blue function is equal to whatever the height of the black one is, plus whatever the height of the red one is. So whenever you're dealing with functions that are a sum of other functions, try and imagine the other 2 functions, and to get the new function, you just add them together. The reason this is important with limits is because we can evaluate limits for functions that are the sum of two other functions if we just know the limits of the individual functions. So for example, let's say we knew that the limit as x approaches some number of f of x was equal to some number, some real number. And then we also knew that the limit as x approaches the same input a of g of x is some other number. This means that the graph of each individual function tends towards a certain value at x equals a. If I asked you what the limit as x approaches a of the sum of their two functions of f of x plus g of x, you'd be able to tell me what it is just from knowing these two things. It would equal L plus M. And the reason this works is because you get the output of this addition of this function, this f of x plus g of x, by adding whatever the value of g of x is to whatever the value f of x is. So if f of x is approaching the output L and g of x is approaching the output M, then whatever this function is approaching is just whatever this function is approaching plus whatever this function is approaching, because the new function is just the sum of the two original functions. All right. So that's the intuition for why we would add these two things together. And using the same logic, it's pretty easy to see why all of the other limit properties work. You'll notice that we have the sum rule here, which is what I just outlined. The difference rule is the same. You take the limit of f of x, which is L, and subtract it by the limit of g of x, M. And it's for the same logic, right? If we know that f of x is approaching L and g of x is approaching M, then the limit of their difference is whatever f is approaching minus whatever g is approaching. Same thing here. We multiply them together. If we have a constant times a function, we take whatever it's approaching times that constant. It's the same thing. It's the exact same logic. And it all has to do with the fact that I'll use the quotient rule as an example. If f of x is approaching L and g of x is approaching M, then the limit, then what their fraction is approaching is whatever f is approaching divided by whatever M is approaching. And M can't be 0 because if M was 0, then the ratio would be undefined. So that's why all these rules work. All you're doing is just realizing that, well, if you're multiplying them together, then you have to multiply their limits together and stuff like that. And I hope the outline of the first example and the multiple examples I gave show why these make sense. There's some other limit properties. The limit as x approaches any input of a constant is equal to that constant. That's because if we have a constant function, f of x equals, geez, that was terrible. F of x equals 4, for example, it's going to produce a straight horizontal line on the xy plane. So we know that no matter the input that this function is approaching, the output is always approaching a height of 4 because the graph is always a height of 4. So the limit as x approaches a of any constant function is equal to whatever that constant is, whatever that number is, for the reason we outlined just there. Additionally, this rule is kind of dumb, but it tells you that the limit as x approaches an input of x is equal to c, or as x approaches c of x equals c, and it might seem complicated at first, but all it's saying is that if we have our function f of x equals x, and we're asking what the limit of our function is as x approaches some value a, we know that with y equals x, whatever the value of the function is at that point, the graph is tending towards it. For example, if I look at this point at x equals a, then we know because y equals x, or f of x equals x, then the height is also going to be a. And we know that the value that it actually is at that point, and for any point, is also the value that the limit, or that the graph approaches. So we can say that the limit, or whatever the graph approaches at a certain input of x, is just equal to whatever the value of the function is at that point. Because for lines, whatever the value is what the graph approaches, as you can see here. Here we have a height of a at this point, and the graph also approaches the height of a from either side. So that's what this means. You can see how this formula is the same thing as the one in the previous slide, just with a's instead of c's. Here's another limit property. It's the same thing as before. If you have some function raised to the r over s power, the limit of that new function is just whatever the limit of the original function is raised to that same power. It's the same kind of logic. If this function is approaching some value L, then if you raise that function to the R over S, then the value it approaches is just whatever the original function was approaching L to the R over S power. The only caveat is S can't be 0 because then the fraction and the exponent would be undefined. And L to the R over S has to be a real number because if a graph is approaching some number or has a limit, then the number it's approaching has to be, a number. So it has to be a real number. So those are the limit properties. The next set of limit rules is the limit of is how to calculate limits of polynomials and their rationals. And it's actually really easy because polynomials, as I'm sure most of you guys have dealt with already, have a cool property that you can basically, any polynomial you can draw with one pencil stroke. It's always connected. It never jumps. It's never disconnected. It's always, we'll get to what this means later, but it's continuous. You can draw it with one pencil stroke. And what that means is that every single point on this graph, if you look at its output, it's also the same value that the graph is approaching from either side. If I pick any point, the height at that point is also what the graph is approaching from either side, which is very convenient. So I want to find the limit of some polynomial, and I'll label this polynomial p of x for a polynomial, as x approaches some input. All we have to do is calculate the value of the polynomial at that input, because the value of any polynomial is also what at a point is also what the graph is approaching at that point. The next example has to do with the ratio of two polynomials. Let's say I had two functions, p1 of x and p2 of x, and I wanted to find the limits as x approaches some input of their ratio of p of 1 over x over p of 2 over x. We would do the following thing. Well, we know that if we want to calculate the value that a polynomial is approaching, we just evaluate the value of that polynomial at a certain input. So what I mean by that is we know that the limit as x approaches a of one of the polynomials is just going to be whatever the value of the polynomial is at that point because of what we said earlier. So if we notice that, well, we say, well, then the polynomial on the top is approaching the p1 of a, the function evaluated at a, and the polynomial on the bottom is approaching p2 of a, because we know polynomials approach whatever their value is at a given point. Then the function you get by dividing one by the other has to be approaching the value of p1 at a divided by the value of p2 at a, because p1 is because the limit as x approaches a of p1 of x is p1 of a, and the limit as x approaches a of p2 of x is p2 of a. All right, so that's what this slide goes over. If you want to look at a more formal definition, I'll lay it out here. This just says what I said earlier. It says if we have a polynomial, if f of x is a polynomial and c is a number, then the limit as it approaches a certain input c is just the polynomial evaluated at that point c. Same here. If f of x and g of x are polynomials and c is a real number, then the limit of their ratio as x goes to c is equal to the function evaluated at c divided by the other function evaluated at c, provided that g of c does not equal 0. Because if g of c was equal to 0, then the ratio would be undefined. So we can't divide by 0. All right. In fact, the limit of most functions as they approach an input can usually be found by just finding the value of the function at that input. This is because most functions approach their actual value at a given point. And we'll go to Jamboard to illustrate this. Most functions you can draw with one pencil stroke. Like this, it's connected, it's never disconnected. All right, so that means that with most functions, whatever the value is at a certain point is also going to be the value that the graph is approaching from either side. And the reason is because if you draw with one pencil stroke, then whatever you're approaching it from either side has to be going to whatever the value is at that point. If you're drawing it in one stroke, you can't. Your drawing has to approach whatever the actual value is at that point from either side, or else it wouldn't be a continuous drawing. So for most functions, if you want to find the limit as x approaches some input c of a function, you can just evaluate the input or the output of the function, I apologize, at c. For most cases, you can do that. The limit is often equal to whatever the value is at that function. I warned you that this is not always true, because remember we defined some weird function. Remember we defined some weird function where we had a line with a hole in it, and at that hole, we'll say the input is x equals 2. It's defined at a point up here, let's say y equals 10. So, or 12, let's just say y equals 12. So for some functions, this is a completely reasonable function. For some functions, the value of the output at a certain point is not equal to the limit. But this is what I like to call a weird function, because we've defined it in a very weird way. And most functions we deal with, most normal functions, and I've used quotations because it's not the best way to describe it. Most functions we've dealt with that aren't defined in some weird way, you can draw them with one pencil stroke. So whatever the limit is, or whatever the graph is approaching from either side of each point, is usually what the value is, or what the height of that point is. So normally we can just calculate the limit by calculating the value of the function at a point. All right. One-sided limits. Sometimes a function approaches a different value from either side of a point. This means that depending on which side you approach it from, the value of the limits will be different. As a result, we use the idea of right-hand and left-hand limits to describe what value a function is approaching from one side of the input. I'll use Jamboard as an example here. Let's say I define some function that looks like the line y equals x up until x equals 2. And then after x equals 2, and including x equals 2, so we'll draw a hole here. So when x is less than 2, but greater than 0, the line is y equals x. But when x is greater than or equal to 2, then the function defining the graph is y equals 4. So if I were to ask you, well, first of all, we notice that this is one of our weird functions because you can't draw it in one pencil stroke. You'll notice that if we want to ask them what the limit of this function is as x approaches 2 of this function, it would be hard to do that. We wouldn't really be able to do it because the function seems to be approaching different values depending what side you look on. For example, on this on the left-hand side, it looks like it's approaching an output of 2, but if you evaluate it from the right-hand side, it looks like it's getting closer and closer to an output of 4. So if we ask what the limit was, which one do we use? It doesn't really make sense. So as a solution to this problem, what we do is we evaluate the individual left-hand and right-hand limits. So if I were to write, and I'll show you the notation over here, and then I'll go back to the example in a second. If I were to write the limit as x approaches 2, and I put a plus sign on the top of f of x, what that means is we're asking what value the function approaches as we get closer and closer to our input from the right-hand side. And the reason we have a plus sign is because the plus sign tells us that we're looking at the right-hand side, or we're looking at numbers that are bigger than our input, more bigger positive than our input. So we look at it from the right-hand side. Similarly, we do the same thing with a minus sign on the top to indicate the right-hand limit. And this number will tell us what value the function is approaching from the left-hand side, or the more negative side, for example. So we go back to this one. If I ask you to tell me what the limit as the function approaches, as the limit as x approaches 2 of this function, but I put the minus sign up top, that would be asking us to find the limit as x approaches 2 from the left of this function. So what it means is we're ignoring the right-hand side, and we're only concerned about what the function is approaching from the left. And we notice that the function is indeed approaching a definitive number from the left. It's approaching 2. So we could say that this limit is equal to 2, and we're all good. Similarly, if we put a plus sign up here, we could evaluate what the graph is approaching from the right-hand side. It's very obviously approaching the value of 4 from the right-hand side. I apologize. So we could say that the right-hand limit is equal to 4. So if you ever see these in problems, it's telling you to evaluate either the right hand or the left hand, and evaluate what the graph is approaching from one side. All right. So back to two-sided limits, we have a little issue. If the right hand limit and the left hand limit disagree with each other, which they do here, then if we ask what the limit as x approaches 2 in general, as x approaches 2 from both sides of our function is, we wouldn't be able to give an answer, because the limit as x approaches 2 of f of x is asking us to evaluate what the graph as a whole approaches. And we can't really do that because it approaches different things from either side. So the function as a whole isn't approaching a definitive number. We get two answers, they disagree with each other. Therefore, the limit as a whole is undefined. There's no answer. We can't give an answer. The answers are in disagreement with each other. So the two-sided limit, we call this a two-sided limit, which is just the general limit without the pluses or the minus, will not exist if the right-hand limit and the left-hand limit are different from each other. It will, however, exist, like we've been showing earlier, if the limits do agree with each other. For example, if I ask you to find the limit of this graph, let's say this height is 2 and the input is 3. If I ask you to find the limit as x approaches 3 of this function, you notice that it approaches the height of 2 from the right, and it also approaches the height of 2 from the left. The left-hand and right-hand limits are in agreement with each other, so the double-sided limit, the two-sided limit, or the general limit does exist and is equal to 2. So that's just covering what we're talking about. This covers what I just said as well. You can stop to read it if you'd like. I explained this as well. Sometimes the left-hand limit and right-hand limit are different, then the limit won't exist. And I explained why this is true as well. So when will a limit fail to exist? We just outlined one case where the limit will fail to exist. The two-sided limit will fail to exist if the right-hand limit and the left-hand limit are different from one another, but it will also fail to exist if the graph isn't approaching anything. And to illustrate this point, I like to use the graph of sine of 1 over x, which is a weird function. If I asked you to tell me what the limit of this function is as x approaches 0, you're trying to answer the question, what value or what height does this function approach as x gets closer to 0? And you'll notice that it's not approaching anything. It just goes up and down and up and down and up and down and up and down. And it's not approaching any definitive value. So we'd say the limit as x approaches 0 of this function doesn't exist because the graph is not approaching any definitive value. So those are the two cases where the limit will fail to exist. All right, so the sandwich theorem for limits is a very useful theorem. The sandwich theorem is a useful theorem for calculating limits that we don't know how to calculate. And the best way to explain the sandwich theorem, I think, is just go straight into an example. Because if I give you the definition at first, it might be confusing. And what we're going to do is we're going to use this new theorem, and I'm going to lay it out to solve the following limit. All right, so we have some weird function, which is x squared times the sine of 1 over x. And this question asks us, what is the value of this function approach as x gets closer to 0? So we notice that at x equals 0, the function is undefined because we get 1 over 0. So we get an undefined answer. But it's still possible. Remember our example from earlier where we had an undefined point. It's still possible for the limit to exist as long as the graph is actually approaching a definitive number. So even though the actual point is undefined, it could still have a limit as x goes to 0. So we're going to try and see if we can calculate it. So the first thing I can do is I can say, well, I know that this inequality is true. I'll explain it in 1 second. And that's because the sign of anything has to be in between -1 and 1. If we remember our unit circle, the sign function tells you the height of the unit circle at a certain angle, all right? And the height of the unit circle can never be greater than 1 or less than -1. So the sign of anything has to be in between -1 and 1. So that's why I can make this inequality. All right. So the next thing I can do is I can multiply all the parts of this inequality by x squared, because if I do the same thing to each part of the inequality, it doesn't change the inequality. So I'll get negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. So what I've done is I've established that this middle function is always greater than this function and always less than this function. All right, pause and take that in for a second. So what I'm going to do is I'm going to say, well, let me calculate the limit as x approaches 0 of the other two functions. The limit as x approaches 0 of x squared, we can look at a graph and see very easily that as our input approaches 0, the height of our graph approaches 0 as well. So we can say that this limit is equal to 0. Similarly, we can also say that the limit as x approaches 0 of negative x squared is equal to 0 as well. Because if we look at the graph here, we notice that as our inputs get closer and closer to 0, our outputs or our height gets closer to 0 as well. All right. So this means that as x squared gets closer to 0, it goes to 0. And as negative x squared gets closer to 0, it gets closer to 0. But in our inequality, remember we said that negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. All right. This means that this function always, I messed up. This function always has to be in between these two functions because we've said it's greater than this one and less than this one. So it has to be in between them. So if both functions are going to 0, that means that this function also has to go to 0 because it's trapped in between them. And we can go on Desmos to illustrate it. So if I have negative x squared here and x squared here, we know from our inequality that our function has to be greater than the black one and less than the black one. And if both are going to 0, you can notice that if the function is trapped in between the two other functions because of our inequality. So if these two go to 0, then our original function must also go to 0 because it is trapped in between the two functions due to our inequality. And if I write out the function on Desmos, you can see how this is true. You can see that due to our inequality is true. Our inequality tells us that the function we defined has to be greater than the black one and less than the red one. So as the two approach 0, that means that the blue function, our original function, is trapped in between the two functions, and it can't be greater than the red one, can't be less than the red one. So if they both go to 0, then that means the blue one also has to go to 0 due to our inequality. And this general process is called the Sandwich Theorem or the Squeeze Theorem. And it's a useful method for solving limits that at first seem very difficult. And I'll go back to the slide and I'll explain the general premise of the Sandwich Theorem. Basically, it says if we can say a function is greater than some other function but less than another function, we're in business, because if the two other functions approach the same value, then the original function must also approach that value too because it's trapped in between them. And I just illustrated about an example of that limit or that process with this limit. All right. It's important to note that our original function doesn't always have to be trapped in between those two functions. In the example I gave, I proved that this function is always in between those two functions, but we don't have to do that for the sandwich theorem to work. All we have to do is show that a function is in between two other functions around the point of interest. So, for example, we're trying to calculate the limit as x goes to 0. So even if we were just able to prove that this function is trapped in between the two functions from negative 0.2 to 0.2, that's enough. Even if it's only in between the two functions for these intervals, that's enough, because it's enough to tell us that it has to go to 0 because it will be trapped in between the two functions as it goes to 0. So even if, for example, the function went down here and then was less than the function over here, as long as we can show that it's in between the two functions at the interval in an interval containing our limit point, then we can use the sandwich theorem. All right, limits involving infinity. Before we dive into this, it's important to note that infinity is not a number, but rather we use infinity to describe the behavior of a function as our inputs get very large. For example, let's analyze why the following limit is 0. So infinity is not a number, it's an idea, and it allows us to represent the behavior of certain functions. All right. So if I ask you to tell me the limit of this function as x approaches infinity, the question it asks is, what value does this graph tend towards as our inputs get very, very large, our x coordinates get very, very large? And you'll notice that the graph of this function gets closer and closer to 0 as our inputs get very, very large. So if we asked what the answer to this limit was, the limit as x approaches infinity of 1 over x, we would say it's 0. And what that limit does is it describes the behavior of x, of 1 over x, as our inputs get very large. It tells us that the bigger numbers we get, the closer we get to 0. So that's why limits involving infinity are often a useful tool, because they describe the behavior of functions when our inputs exceed all finite bounds. Yep, if a function approaches a certain number as x goes to infinity or negative infinity, negative infinity just means that we're getting really large negative numbers. So like negative, you just keep going to the left. If our function approaches a number as x goes to infinity or negative infinity, we'll have a horizontal asymptote at whatever height it approaches. It's pretty obvious to see why this is true. I'll draw a line here, y equals 0. If our function as x gets large approaches 0, then by definition, the line y equals 0 has to be a horizontal asymptote, because by definition, an asymptote is a line that the graph approaches, and the graph approaches 0. So the graph will also approach the line y equals 0. So it's not too hard to understand that. But all it is using the idea that if limits approach a certain number, then it must approach the horizontal line at that number. So we can say that if a limit exists as x goes to negative infinity or positive infinity, then there's a horizontal asymptote at whatever number it approaches, using this logic. As a result, a function could have more than one horizontal asymptote, because a horizontal asymptote, and I'll show you what I mean by that in a second, is because a horizontal asymptote exists if the limit as x goes to infinity is a number, or if the limit as x goes to negative infinity is a number. And if these two limits exist, if our function approaches a value as x goes to infinity and negative infinity, but they're different from each other, then our graph will have two horizontal asymptotes. And I think, yeah, this is it. You'll notice that this graph has two horizontal asymptotes at y equals 1 and y equals negative 1, because it has two limits as x goes to infinity and negative infinity that are numbers, but they're different from each other. So that's a scenario where a graph could have two horizontal asymptotes if they have two limits, but they're different from one another. Additionally, a graph could have no horizontal asymptotes because the limit is not a number. For example, x squared doesn't approach any finite number as x gets really large, so there's no horizontal asymptote. All right, the sandwich theorem for limits at infinity still works, and it's just the same premise. If you can trap a function in between two other functions as their inputs get super big, if the two other functions approach the same number, the original function must as well. It's the same kind of logic. For example, I can show. I'll explain the sandwich theorem by yet again doing another example. For limits at infinity, what we're going to do is we're going to calculate what the graph of sine of x over x approaches as x gets really large, what value it approaches, using a new theorem. So we know that from our previous example that the sine function has to be greater than negative 1, but less than 1. So we can make this inequality. Then I can divide every side of the inequality by x, because as long as I divide each part of the inequality by the same thing, it doesn't change the validity of the inequality. And then we get a similar thing to before. We have that our function is always trapped in between two other functions. It has to be greater than this function and less than this function. And you'll notice that the two functions I've outlined here, if I erase my other two functions, they both approach 0 as x goes to infinity. And our graph is trapped in between the two of them for our inequality we've established. So if the two of them go to 0 and this other function is trapped in between them, then the other function must go to 0. So as a result, we can say the limit is equal to 0 by the sandwich theorem. So basically, it's a long way of saying that the sandwich theorem still works for limits going to infinity. And if you want, what I'll do is I'll write the graph of sine of x over x, and you can see how sine of x over x is always trapped in between these two functions because of the inequality we've established. So it's also going to 0. As x gets really, really large, you can see that it's getting very close to 0. All right. Next topic. Good news. Our limit rules still hold from earlier on. They're true for the same reasons I outlined before. And I wrote this for my class, but I'll kind of quickly go through why they still work on a Jamboard. If you had a function, let's say you had a function f of x that that as x goes to infinity, I'll write this in a better way. That as x gets really, really big, the function approaches 2. All right. And let's say if you had another function, g of x, that when x got really, really big, it approached 3. Then the limit of, as x goes to infinity, of g of x plus f of x is yet again whatever value g is approaching plus whatever value f is approaching. So it'd be 3 plus 2 equals 5. So with the same logic, we can show how every other limit rule we outlined is also true for limits involving infinity. It's the same kind of process. All right. Infinite limits as x approaches a. Sometimes a function gets closer to an input. All right. Sometimes, as a function gets closer to an input, the output approaches positive or negative infinity. For example, let's look at the function f of x equals 1 over x as an example. I'll go into Desmos actually. So you'll notice that as the graph approaches the input of 0, from the left, it goes to negative infinity. The output goes really, really large. And from the right, the output gets very, very big. It goes to positive infinity. So to represent that mathematically, what we do is we write that the limit, and I'll write it this way. So we'll notice that from the left-hand side, the function 1 over x gets closer and closer to negative infinity as we get closer to 0. I could write a left-hand limit and say that the limit as x approaches 0 from the left of 1 over x is equal to negative infinity. And yet again, infinity is still not a number, but it rather just tells us how the function is behaving as we approach 0 from the left. It tells us that we get more and more and more negative. Similarly, I could say that the limit as x approaches 0 from the right of our function is infinity. And same as before, it doesn't make sense I'll backtrack really quickly, 1 second. Yet again, it doesn't mean that it's equal to infinity at x equals 0. It just means that as we approach 0 from the right-hand side, our outputs get bigger and bigger and bigger. So this is only just a way to describe the behavior of the function. But we'll notice that with the way we've written things here, the behavior of the function as x goes to 0 is different on either side. On one side, it approaches negative infinity, and on the other side, it approaches infinity. So the two-sided limit as x approaches 0 of 1 over x, we would say doesn't exist because the two behaviors disagree with each other. If, for example, on both sides, they approached infinity, and an example I can use here is the graph of 1 over x squared, then we could say the two-sided limit exists because both sides are approaching infinity from either side. So we could say the two-sided limit is also equal to infinity. It goes, the outputs get larger and larger and larger from both sides. But for 1 over x, we can't say that. One gets really negative, one gets really positive. So the two-sided limit does not exist. All right. Let me make sure I covered everything from this slide. All right, so the next thing is, it's also a useful tool. It's also a useful tool defining limits in this way by saying that, well, if we notice that our graph is getting really large around an input a, it's useful to define the limit as equal to infinity because it tells us behavior, but it also tells us the existence of a vertical asymptote. And a vertical asymptote is a line that the graph gets closer and closer to, but doesn't touch. And you'll notice that whenever a graph gets closer and closer to negative or positive infinity around a certain point, that what it's doing is it's getting closer and closer and closer to touching this line, but it never actually touches the line. Because if it did touch the line, then we would say that wherever it intersects the line is the value of the limit. But it doesn't. So that means that the function has to go lower or higher and higher and never touch the line, the vertical line at that point. So as a result, if we evaluate a limit, or either a right-handed limit, a left-handed limit, or even just a general limit, and we get infinity or negative infinity, it tells us that there's going to be a vertical asymptote at that point. So if the point we're evaluating is at input A, then the vertical asymptote will be the equation x equals A. That's useful to know. And you can read this if you would like. All right. Same thing as I said before. If the two-sided limits disagree with each other, then if the one-sided limits disagree with each other, then the two-sided limit will not exist for the same reason we outlined earlier. All right. So, and behavior models is the last topic we have to cover today. We don't have a lot more to cover, which is nice. So I'll show you I'll read this out, and then I'll show you the concept with an example on a Jamboard. All right. So sometimes when we have crazy functions, I think you'd agree with me that it's useful to use a much simpler function that acts like the original function to describe its behavior. This is especially useful if we wish to understand how a function behaves as inputs get very large. All right. So I'm going to do a bit of algebra on Jamboard to illustrate why and behavior models, and we don't know what they are yet, but I will explain what they are a useful mathematical tool. So I'm sure you'd agree with me that if we took a number x and divided it by some other number y, and we said it was equal to 1, this would mean that x must be equal to y. And you can show this by multiplying both sides by y, and you'll get that x equals y. Right? So when x divided by y, or a number divided by another number equals 1, the two numbers must be equal to each other. So I'm going to use an example. I'm going to give some crazy function. We have 3x to the fourth plus 10x cubed plus 10x squared plus 10x plus 10. All right. And obviously this is a crazy polynomial function. That's kind of weird. And if I asked you to tell me what its end behavior is like what does it look like as x gets very large? Does the function go up to infinity? Does the function go down to infinity? Does the function approach some number? If I asked you to tell me that, you might go like, well, I have no idea. This is some crazy function. I have no idea what the graph is going to look like as our inputs get very, very large. So the solution is to make a much simpler function that acts like the original function as our inputs get very, very large. And to show that two functions act the same as our inputs get very, very large, we can actually just use the ideas of limits, which is very cool. All right, so I'm going to outline a limit, and then we're going to look at it, and we're going to make sense of it. I'm going to evaluate the limit as x approaches infinity of this crazy function plus 10 over its first term, its biggest term. All right. So what this means is it's asking us to evaluate what the ratio of these two functions is as x gets very large, as our inputs get very, very large. All right. And if we find that this limit is equal to 1, what this will tell us is that as x gets very large, these functions are the same, because something divided by another thing, if it equals 1, they're the same. So if this limit equals 1, it tells us that as x gets very large, these two functions are the same. Right? So what we can do is we can do some algebra here. We can divide each term by the denominator individually because that's a rule in algebra we can do. So we can rewrite this. We can rewrite this fraction as 3x to the fourth over 3x to the fourth plus 10x to the third over 3x to the fourth, et cetera, et cetera, et cetera. And what we're going to get after we do that is we're going to get that the fraction is equal to 1 plus 10 over 3x plus 10 over 3x squared plus 10 over 3x cubed plus 10 over 3x to the fourth. All right. So our crazy function divided by 3x to the fourth is equal to this here using some algebra. So the limit of this ratio is also going to be equal to the limit of this thing right here, the limit as x approaches infinity of this thing, because we showed algebraically that this is the same thing as this. All right. And to evaluate the limit, we can just ask ourselves, well, what happens to this as x gets very, very large? Well, as x gets very, very large, each term has an x in its denominator. So as x gets very big, the fraction is going to get smaller and smaller and smaller because our denominator gets huge, which means that our fraction gets closer and closer to 0. So each of these terms as x goes to infinity is approaching 0. So we can say the limit is equal to 1 plus 0 plus 0 plus 0 plus 0, which equals 1. So we prove that the limit is equal to 1, which means that this very simple function actually perfectly models what this function looks like as our outputs get very large, because our limit showed them that they equal 1, and therefore they act the same as x gets very large. So this is useful because I'm sure you could tell me what the graph of 3x to the fourth looks like as our outputs get very large. As we let our outputs get very large in 3x to the fourth, our graph goes up and up and up to infinity. So you could say as x gets very large, the end behavior of 3x to the fourth is that it goes to infinity. Another way you can write this is the limit as x approaches infinity of 3x to the fourth is equal to infinity. And yet again, infinity is not a number. It's just telling us information and describing how it behaves. It tells us that as our inputs get very large, the outputs of this function get very large as well. And because 3x to the fourth describes this function very well, it also tells us that the limit of this function as x goes to infinity is also infinity. The end behavior is the same. So that's what we mean by end behavior models. We can make simpler functions to describe more complex functions by showing that they're the same as our inputs get very large. So I'm going to go back to my slides here, and this is just saying the same thing. All right, and so with that, geez, I just had a brain fart moment. With that, we can generalize our definition of end behavior models using the example we just used. And it's that if we have a function f, a crazy function f, then another function g is a end behavior model if their ratio is, if you take the limit as x goes to infinity, if it equals 1. And there's two kinds of end behavior models. There's a right end behavior model and a left end behavior model. And we use different limits to describe them, and I'll explain why in just a second. If we show that as our outputs get larger and larger and larger in the positive direction, if our inputs get larger and larger and larger in the positive direction, and the ratio of the two functions when that happens is equal to 1, that means that the function g acts like the function f as x goes to infinity. So the end behavior model, or what it looks like as we go to the right, of our original function is g. G will tell us what f will look like as x goes to infinity, or x goes to the right. Similarly, because as x goes to negative infinity, our inputs go farther and farther to the left. So if the ratio of the two functions as x gets to negative infinity is 1, the two functions will act the same, and then g will be a left end behavior model for f. Additionally, if the right end behavior model and the left end behavior model are the same, we just call the general function a end behavior model. All right. So for polynomials, using the proof we did for the first polynomial, the same logic, we can show that the term with the highest degree in a polynomial is this end behavior model. So similarly to how with our example on the Jamboard, we showed how the first term that had the highest exponent, 3x to the fourth, was the end behavior model. We could do the same process for any polynomial to show that the first term with the highest degree is its end behavior model. All right. So end behavior model for polynomial rationals is also pretty simple. And I'll explain why in just a second. If I asked you to find the end behavior model for the ratio of two polynomials, let's say we have 3x squared plus x over 4x cubed plus 5. If I asked you to find the end behavior model of this function as a whole, it's asking us what does the function look like. I won't write it out, it's too much, I'll just say it out loud. It's asking us, well, what does the function look like as our outputs get very, very large? So let's imagine we're trying to find a right end behavior model. All right. That means we're asking, what does this function look like as our inputs get very large and we go farther and farther to the right? So we can approach this by looking at the top and the bottom and realizing, okay, well, these are polynomials. And we know that as our inputs get very, very large for the top polynomial, it just equals its end behavior model. We know that an end behavior model for the top one is 3x squared, because that's the term with the largest exponent. So as our inputs get very large, the top function becomes indistinguishable from 3x squared. Same with the bottom one. As x gets really large, the bottom function becomes indistinguishable from 4x cubed. All right. So we could say that an end behavior model for this fraction is just you divide the end behavior models of the numerator and the denominator, because as x gets large, this top function is equal to this. As x gets large, this bottom function is equal to this. So as x gets very large, then the ratio of the two functions is just the end behavior model divided by the end behavior model, which equals, in this case, 3 over 4x. This would be the end behavior model for this function. So in general, I think I outlined it here. If we have a function that is the ratio of two polynomials, its end behavior model can be found by dividing the end behavior model of the two polynomials. End behavior models are useful because, for example, if we find out that an end behavior model, let's say we're finding the end behavior model of a certain polynomial, a certain rational function of polynomials, which just means you take a polynomial and you divide it by another polynomial. If we found that an end behavior model for it was equal to some number, that means that as x gets very, very large, this ratio looks like the function 4/5, which means that it looks like y equals 4/5, right? And that means that it approaches the value of y equals 4/5. As x gets very large, it becomes indistinguishable from the value of 4/5. And remember, when we're dealing with limits at infinity, we said if a value gets closer and closer and closer to being a certain, if a graph gets closer and closer and closer to being a certain output as x gets very large, we say that the horizontal line there is a horizontal asymptote. This is the same logic. If the end behavior model is a number, that means that end behavior model is a horizontal asymptote, because the graph gets closer and closer and closer to looking like that function as x gets very, very large. So that's a useful use of end behavior models, because you can use it to find horizontal asymptotes of rational polynomial functions if they exist. So the last slide is useless. I don't know why I put it there. You can read it if you like, but that's it for today. Thank you guys for tuning in. I hope to see you guys in the next video. If you have any questions, please leave them in the comments below, and I will try and answer them. And I'll see you guys next time. Thank you once again.